I've not been idle in recent weeks and I've updated my Pendulum. I've got it to work quite nicely, as you can see. Yeah, let's go over the changes I've made and explain what I did. Well, first of all, the most obvious change that I made is that I've shortened the length of the pole. I had the idea that the longer the pole, the easier it would be to balance, just out of experience. If you balance something on your fingertip by hand, it's easier the longer the object is, but in this scenario, in this setup, the shorter pole works better and it's much more impressive because it can lean much further and still catch itself compared to the long one. The next addition that I've made is that I added from an old RC a joystick controller to control the linear position of the card. So I can control it now, control where it comes to a halt. And that's just a gimmick in the end. So what you can see here is the backside of the Pendulum. You can see that I've attached the Arduino and the motor driver to the printer, and I've also cleaned up all the wiring and made it permanent. And so at this point, what I can do is I can carry the whole unit around and I'm mobile with it and take it to places and show people. I've also added a board for my potentiometers. So you can see here all the potentiometers with the different gains. I've also added a button to enable or disable the potentiometers. So right now I have the working gains saved in the software, and it takes these working gains. But if I want to demonstrate to people how the pendulum behaves at different gains, I can just enable the potentiometers and then the gains will actually get taken from these. So now to the main part of this video, and that's how I improved the performance of the pendulum the way I did. Because as you can see, it's working much better right now than it was in the previous version. You can see that it's really stable on the linear position, so there's barely any movement at all to keep it at its position. And it's also much more robust to outside disturbances and to bumps. So, and it still catches itself. And it's also reaching its linear position and standing still quite fast, if you ask me. There's mainly 3 reasons for that, how I improved it. And the first one is that I've shortened the pendulum, as I said before. So the second and probably the main reasons I've had issues with the performance here has to do with the sample time of the PID controller. Well, the sample time is something you define through the library, and it basically defines the interval at which the controller is supposed to run. So in my example, I've chosen 2 milliseconds, and that means that every 2 milliseconds the controller is expected to run time and calculate a new output value for the motors. What you have to understand is that the controller is called inside the loop of the Arduino. And the issue that I figured out I had was that a whole loop of the Arduino code took longer than this defined sample time. In my example, I took about 50 milliseconds for one whole Arduino loop, but defined a sample time of 2 milliseconds for the controller. And what the controller internally does is pretty much every time the controller code is called, it basically checks, have 2 milliseconds passed since the last time I was called? If so, execute the whole controller code. So what that means is a loop takes 15 milliseconds, and that means every single loop the controller is called because more than 2 milliseconds have passed. The problem with that is that the defined sample time that I've defined by 2 milliseconds is used for internal calculations in the library. So it's basically used to calculate the D and the I parts of the controller. So those are time-dependent values, and the controller just assumes that it's running at 2 milliseconds basically, and uses these 2 milliseconds as a basis for its calculations. The thing is, it doesn't run at 2 milliseconds, it runs at 15 milliseconds. And so all the calculations for the D and the I part are just rubbish. You can throw them out the window, they're not worth anything. That's what the problem was. So the goal was to decrease the whole time that the Arduino loop took. And the main culprit that I figured out here was the serial output. So before now, I've put out all kinds of data through the serial monitor, and that took time. So I've just commented out all my serial outputs and bang, it worked. That reduced the sample time to under 2 milliseconds and made everything work. So that was the main reason it wasn't working. So the third issue I ran into had to do with the D part of the linear controller. And I'm going to show you the problem that I faced because I can recreate it by using my potentiometers. So what I'm going to do now is I'm going to enable the potentiometers so that the gains get taken from these and not from the saved values. And at first glance you don't see much of a difference, but it will come apparent when I bump the pendulum. You can see that it still catches itself and stabilizes itself, but it won't come to a stop. So what you'll see is it'll oscillate back and forth around the linear set point, and eventually it will come to a halt, but it just takes forever. And that's just not an acceptable performance. And usually when you see a problem like that, you'd think that increasing your D gain should solve this problem, because that's exactly what the D gain is for. It's there to limit overshoot and dampen oscillations. So that was the first thing I tried, and I'm going to show you what happens if you increase the D gain. So now I've increased the D gain to a value where it would potentially solve my overshoot problem, but you're going to see what happens if I bump the pendulum now. You see, the pendulum goes nuts. It just goes back and forth, the movement becomes jerky, and it just oscillates out of control. So I'll disable the potentiometers and go back to my saved values. And so the problem you're facing here is, in theory, what you should do is increase the D gain. But if you increase the D gain, your pendulum just goes nuts and it doesn't work. So what the problem basically comes down to is the relation of the resolution of my linear measurement and the fast sample time. So I have about a linear resolution of about 9,000 steps over the whole length of this pendulum. So let's say 9,000 steps over 25 centimeters. And I'm calculating the linear speed by using the position, the last position, and the current position divided by the time span that has passed, divided by those 2 milliseconds. And what happens here is the resolution is just too low for this fast of a sample time. Or, in other words, the sample time is too fast for the resolution, for the low resolution of this linear encoder. And that introduces noise to the D signal, because what happens is, even at full speed probably, within this one cycle of 2 milliseconds, the card probably hasn't moved a single step. So the linear speed signal is actually 0, even though it's probably moving at full speed. And in the next cycle it probably has moved 1 or 2 steps. And so essentially the speed jumps up to whatever, really high. And so you get this spiky signal, this noisy signal, and you've got a really low signal to noise ratio. And what that means is the input signal for the D part is noisy, and that will result in a noisy output of the D controller. And that makes the overall output to the motors noisy, and a noisy output means a jerky movement, and a jerky movement means a lot of speed changes, and a lot of speed changes again mean that the noise in the depot increases even more. So what you've got here is you've got kind of a feedback loop that oscillates out of control. So what's the solution to this problem? Essentially what I did is I averaged out the linear speed signal. So I'm not taking the linear speed or calculating the linear speed over a span of 2 milliseconds, but I'm averaging it out over 50 controller cycles. That means 100 milliseconds. So the speed now gets calculated over a span of 100 milliseconds, which basically filters out all that noise and really comes up with a good representation of the real speed. And that smooths out the noise and therefore the D part, and results in a great performance. So as you've probably seen before when I showed you the potentiometers, there's a 7th potentiometer now that's called lean KD average, and that's essentially the gain for that part. And as you can see, if I bump it now, it will come to a halt much more quickly in the middle without oscillating back and forth forever. Yeah, and that's what I've done and what I did to solve the problem. So that's essentially it. I think this project is probably finished, and last thing that comes to mind is the swing up, so that the pendulum would swing up itself, but I couldn't figure a real reliable way out to do this yet. I managed to do it a few times, but what I did is I just hard-coded the movements of the card into the Arduino. So I just said move the card with speed 200 to the right for 200 milliseconds, stop and move to the left for 400 milliseconds or whatever, and created a movement that would essentially swing up the pendulum. And that worked, but it's real tricky. The problem of that is that you really have to be careful, so the pendulum has to come to a stop almost from alone. So you can't have it swing up and have much speed here at the top, because then the controller won't be able to catch it. It basically has to swing up and come to a stop from itself so that the controller can catch it. And the next problem is, because I've just simply hard-coded the movements, even the slightest change of the setup makes it not work anymore. So it might work one day with the same movements, and the next day when it's 2 degrees colder or 2 degrees warmer, it won't work anymore. Because there's no feedback control in this system. So even if I place just a playing card under here and so elevate this side a little bit so that it stands at the slightest angle, it won't work anymore. And so I have ideas to figure that out and to create a controller for that, but yeah, that's in the future and we'll see how that goes. So that's it from me, and yeah, hope you enjoyed. Goodbye.